discuss how to actually run and interpret confidence intervals when we're working with two different proportions. So when we have our two different samples that we want to compare, how do we create the interval and then how do we interpret the interval? So when we run confidence intervals, again, confidence intervals are a little bit different than tests in that with a confidence interval, the whole reason we're creating a confidence interval is because we have no idea about the population value. So we don't know what the population proportions look like. We only have sample values to work with. And so using those sample values, because our sampling distribution has the three properties that it does, we're able to use that to create an interval that gives us plausible values for our population value. Okay? So when we come from two independent random samples, or two groups in a randomized experiment, the p-hat, or the p-hats that we collect, so p-hat 1 minus p-hat 2, that's our best guess at what the true difference in proportions would be. So we use that best guess and some of the ideas that we've talked about in the previous chapters, and we can create an interval that gives us a plausible value. So what could our true difference be? So we go back to our formula from chapter 8. So we have our sample statistic, plus or minus the critical value, which is based on Z star, T star, those are the critical values, but how do we determine what do we have to use in order to determine which critical value we're working with? Well, mean, we'd use T, proportions, we'd use Z, but how do I know what exact value I need? And in order to look it up on the table, I would need the confidence level. Okay? So your critical value is determined by your confidence level. So when we're creating these intervals, remember we have a confidence level, how sure we are that our interval captures the true proportion, or in this case, the true difference in proportions between our two groups. Now, the statistic in this case is the difference that we calculate from our samples. So that's our P1 minus P2 based on the sample values. Okay? So when we plug in our information here, p-hat 1 minus p-hat 2 is your statistic. Since it's a proportion problem, the critical value would be Z star, and is determined by our confidence level. And then when we say standard deviation of the statistic, that's actually talking about what? Standard error. And how do we find standard error? That's our formula here. Now this is the standard deviation for our entire distribution. If we convert to an interval, though, we don't have population value. So instead of P and Q, we use P hat and Q hat. So P hat 1, Q hat 1 over N1, P hat 2, Q hat 2 over N2. So when we're working with intervals, we only have sample values at our disposal, so that's the only thing we can use to run any of our calculations. Okay? So as far as creating the interval goes, it's exactly the same as what we discussed back in chapter 8. Okay? So the other thing that's nice is that the conditions for inference are exactly the same. Now, as far as checking our conditions, when we check the random condition, we're still looking at the fact that we need random samples, so they need to say that we got a SRS or we had a randomized experiment. The other thing that you need to kind of keep in mind here is this idea of independence. When I take the two groups, I need to be fairly certain that the two groups I selected are independent of one another. So one group is not going to affect the other group. Okay? And that's just something you kind of think about or justify within the scenario itself. So when we look at those two groups being selected, would there be any reason to suspect that they would influence each other. Okay? If you do see something there, then you wouldn't want to proceed with these procedures. But if there's nothing there that draws any red flags, then you would just go as you would normally. So you have to have the random sample, just like always. 10% says that our sample sizes have to be less than 10%, and that has to be true for both samples. So since we have two different samples now that we're working with, you need to make sure that n is less than 10% for both groups. Okay? And then finally, that success fail, or what we call the large counts condition. So this is the success fail, or your book calls it the large counts. So on this one, NP hat and NQ hat for both samples needs to be larger than 10. So you need to check NP and NQ for sample 1, check NP and NQ for sample 2, make sure that they're all at least 10. So, when the three conditions are met, you can calculate your interval using the following formula. Now, just like before, when we did confidence intervals for proportions and means, there's a formula for it and there's a way to do it in your calculator. You need to know how to work both. Okay, so you need to know how to work the formula because, again, there might be times where they give you an answer in formula mode. And so you need to understand where each of those pieces comes from so you're able to match it up correctly. So this is the formula. Take p hat 1 minus p hat 2. That's your statistic. This is our sample difference. We have our critical value, which for proportions is z star. That's determined by confidence level. So if we wanted a 90% confidence interval, z star would be 1.645. So those are ones you might want to go back and review. Just looking through the tests here, some of you guys missed points because you were putting the incorrect z stars into your formulas. You need to make sure you know what those are. So 90%, z star would be 1.645. For 95%, 1.96. For 98%, anybody remember that one? That's 2.33. And then 99% was 2.576 or 2.58. Okay? So if you don't remember those, you need to go back. I would just memorize those main ones because those are ones you're going to see most often. If you don't get a value that you know off the top of your head, what function in the calculator gets you your actual value? Inverse norm. So if you want z star, you can use inverse norm. Now, when you do that inverse norm, remember it asks for area. Area is the confidence level plus whatever's left in one tail. So make sure if you're plugging in for 95%, for instance, you would have 95 plus 2.5 in each tail, so you'd have 95 plus 2.5. So you'd actually type in 97.5 for the area. Okay? So make sure you're able to do that based on any confidence level. And then standard error is just your p hat, q hat for both samples over their respective sample sizes.
Is there, like, are we going to learn a calculator way to solve this, or is that the only way?
Nope, we're going to learn calculator way as well. Okay? Now, when everything's met and we create this interval, we're creating what we call a two-sample z interval. So we had two samples to work with, z, because we worked with proportions. And then we created an interval for the true difference between P1 and P2. So we use the sample values to create an interval that hopefully captures the true difference of the actual proportions. Okay? So, if we look at an example, among randomly sampled teens aged 15 to 17, 57% of the 248 boys had posted online profiles, compared to 70% of the 256 girls. what does a confidence interval say about the difference in online behavior? Okay, so we want to construct and interpret a confidence interval, in this case, for the difference in proportion of boys and girls who have online profiles. Okay, so we have two separate groups that we're trying to compare. So when we want to work our confidence interval, the first thing we have to do is check our conditions. So for our conditions, the data would come from random sample, so it says randomly sampled teens. As far as boys and girls are concerned, as far as online profiles, would boys and girls have any sort of relationship? Would they be affected by what proportion does whatever? No. So they'd be two independent groups. Okay. For our 10% condition, again, we have to check both groups. So 248 would be less than 10% of all boys aged 15 to 17. 256 would be less than 10% of all girls aged 15 to 17. So check both sample sizes and make sure that they're less than 10%. When we go to our success-fail or our large counts, we do NP and NQ for both. Now in this case, notice I'm using just a little bit different notation. Instead of N1P1 and N2P2, I just used B and G. So B for boys, G for girls. That way we don't have to keep going back and forth. Well, did I make girls or boys number 1 or girls or boys number 2? So you can use the lettering to differentiate as well. Now the other thing, and this is one again, some of you guys missed points on this last test, was when you do N times P, in a lot of cases or a lot of problems, when they tell you, so like in this problem, if they had said 141 of the 248 boys had online profiles, that 141 is your NP. So I had some of you guys calculating P, multiplying it by N, and then giving a decimal answer when we know how many there actually were. Okay? So you got to pay close attention to the problem. If they give you NP, that is your NP. You don't have to actually calculate it. Okay? Now, if we do have to calculate it, so this time they didn't tell us exactly how many boys had online profiles, they gave us a percentage. Then we do actually have to do N times P. Now, in your calculators, if you take 248 times 0.57, so do that real quick. What do you actually get? So 141.36, right? Now, what we're looking at here is we're looking for the number of successes within our group. Now, if I were looking at the 248 boys, could 141.36 boys have online profiles? No, because you can't have 0.36 of a person, right? So you have to round to the nearest whole number. So 141.36 would round it to 141. And then we do the same thing when we do NQ. So we need to do that for both, because with these proportion problems, when we get decimals, remember in our calculator, it's not going to accept decimals for an x value. So when you check your conditions, make sure you're rounding to the nearest whole number when it's something that needs to be a whole number. So we need to have a whole person to be accounted for. Okay with that? Okay, so this is what your conditions should look like. So random, show that it's random, or say that it says it was random independent. Check both sample sizes for 10%, and then check NP and NQ for both groups, and make sure they're at least 10 in each case. Okay, so once we've done that, we can go ahead and set up our interval. Now, the way you subtract, because remember, subtraction is not commutative. If I subtract one way, or I switch or flip the order and subtract the other way, I'm going to get different results, because one would be positive, one would be negative. So when you choose the direction in which you're going to subtract, you need to dictate what direction you did. So in this case, I chose to do the proportion of girls minus the proportion of boys. Why do you suppose I chose that direction? because it's going to give me a positive value, or it's more likely to give me a positive value. So when I look at my sample proportions, 70 minus 57 would be positive. Positive's usually easier to work with than negatives are, okay? But at this point, I could have just as easily said the proportion of boys minus the proportion of girls. The only difference is my interval will be positive or negative once I finish up, okay? So that's one thing you have to be careful with here, that we didn't have to concern ourselves with one proportion. We have to determine what direction we're going and then make sure we show exactly what direction that is. So the formula would say, take the sample proportion of girls minus the sample proportion of boys, plus or minus our critical value, times our standard error. Okay? So, what that looks like, our sample proportions were 70 and 50%, so 0.7 minus 0.57. Plus or minus, if it's a 95% confidence interval, Z star would be 1.96. For the variance for girls, we would take our proportion, 70 times its complement 30, divided by the sample size, 256. Do the same thing for boys, 57 times 43%, divided by 248. Now again, when you go to type this in your calculator, make sure you do this addition first. So either make sure you have parentheses around the entire thing inside the square root, or do the addition first, then take the square root of that answer that you received. Okay, so do the addition first, then take your square root. And so once you do that, and simplify it all down, we get an interval of 0.0466 to 0.2134. Okay. Now, at this point, we would need to interpret what this confidence interval says. So previously, when we were looking at one proportion, we would have said we're 95% confident that the true proportion of whatever was between, in this case, 4.6% and 21.3%. Okay? Or we would have said we're 95% confident that the true proportion is captured by this interval or whatever. Okay? But now we have to account for the fact that these proportions are differences. These are the difference between one group and another. So, when we go to interpret this, we start off pretty much the same way as we always have with intervals. We're 95% confident that among teens age 15 to 17, so make sure we stipulate what our population of interest was. So we're 95% confident that among teens age 15 to 17, the proportion of girls who post online profiles is between 4.7 and 21.3 percentage points higher than the proportion of boys who do. Okay? So when we think about our interval, okay? So this was our interval. We have to think about, well, we took girls minus boys. So when it comes out entirely positive, that means the proportion of girls was larger than the proportion of boys. So when we do our interpretation, we can actually say that the girls who post online profiles is between 4.7 and 21.3 percentage points higher than the proportion of boys. If we had done this in the reverse order, so if we had done boys minus girls, what would have happened is our interval would have looked like this. So it would essentially be the exact opposite, so negative 0.213 to negative 0.047, in which case we would say that the proportion of boys who post online profiles is between 4.7 and 21.3 percentage points lower than the proportion of girls. Okay. So the second part, now this first part is truly the interpretation I would want to see from you guys. So we're 95% confident that, and then insert the context. Okay. The second part is just another statement you could make to kind of clarify what this means then. It seems clear that teen girls are more likely to post profiles than are boys the same age. So that's just something else you could put in to kind of clarify what that means. Okay? So when you look at your interval, if it's entirely positive, that means that the first proportion that you worked with, so whatever you did 1 minus 2, proportion 1 was larger than proportion 2. Or if it's all negative, that means the exact opposite. Now, if we did this same exact problem, but let's say we came up with an interval like this. So when we did our steps, we had a negative to a positive. So if we get something like this, our interpretation changes just slightly. So we'd still start off, we can be 95% confident that among teens aged 15 to 17, the proportion of girls who post online profiles is between 4.7% lower and 21.3% higher than the proportion of girls, or the proportion of boys. So when you have a split interval where part of it's negative, part of it's positive, you need to account for that when you run your comparison. So the proportion of group 1 is between 4.7% lower and 21.3% higher than the proportion of group 2. Okay? So as far as interpreting goes, you have to talk about that difference between the two groups now. That's the only major change between this and what we've done before. We okay with that? Okay. So, that's it.